Multiplayer gameplay development is tough, and one of the struggles developers have to overcome is packing a lot of data into little packets. I wanted to go over how data is sent over the network from the authoritative server to clients for my hybrid rollback and authoritative server network architecture. Entities in our game are built from several different components, and all of this data needs to get from the server to the clients somehow. One way we cut down on how much data is sent is by only sending things that change on a given frame, such as just the movement component. But the main way we cut down on the size of packets is through bit packing data into the packet. The packet is just an array of bytes. In our case with GDScript, it is a packed byte array. Just like the name sounds, a packed byte array is an array of bytes. So, let's get some in there to work with. A byte can represent an integer between 0 and 255. Its hexadecimal representation is 2fs, and it is comprised of 8 bits that can either be 1 or 0. If we were to simply write a bool into the byte array, that bool would have a value of 1, and the wasted space is obvious when looking at just the bits. We are only using an eighth of the space available. To pack data into this buffer, we start by writing data into a scratch variable. The scratch variable is a 64-bit integer, so its values range from 0 to 2 to the 64th minus 1. Here's the hexadecimal representation. And here it is as bits. Let's make that a bit smaller. We break this scratch up into two different segments. The first 32 bits are what we will write to the buffer, and the last 32 bits are for overflow. Let's take a look at what it's like to write some data to be sent. Here are some arbitrary values that we want to send over the network. Once we have all the data we want to send for a given frame, we can start writing that data to the buffer. Here's our first value, represented as bits. We only need 11 bits to represent the value, so we will write this into the scratch. We first check to make sure that we are writing 32 bits or less at a time. Then, since this is the first time we are writing to the scratch, the number of scratch bits is 0. So, the scratch is bitwise ORed with the data. Pretty simple. After that, we add the number of bits to the scratch bits, and track the total number of bits we are writing into the buffer. Now for our second value. This one takes up 18 bits. When we write this value, we start by shifting it 11 bits to the left, then ORing this new value into the scratch. Then we track the total bits and the number of scratch bits and move on. Our scratch now has 29 bits in it, tightly packed with the first and second values. Now let's go on to our third value. Again, we start by shifting it based on the current scratch bits, followed by ORing the new value into the scratch. Our scratch now has all three values tightly packed, but now the number of scratch bits is greater than 32, so it's time to write data into the buffer. To write data into the buffer, we feed the scratch into this function and take the bottom 32 bits. Each word is built from 4 bytes, so we find the index within this buffer to start writing data. After that, we write each of the 4 bytes from the word into the buffer. After that, we advance the word index by 1. Now that the bottom half of the scratch is in the buffer, we decrease the number of scratch bits by 32, and shift the scratch to the right by 32 bits. After the scratch is shifted, we tally up the total number of bits we have in the buffer. If this were all the data we wanted to write, we finish by flushing the scratch to the buffer. This occurs just like before. There might be some unused bits at the end, but that's fine for now. Now we have all the data tightly packed into the buffer. The only unused bits are whatever is left over during the last flush into the buffer. Once all of the data is packed away, we add on a few more bytes at the end of the buffer, so we know how many bits were used when decompressing the data, and some other important information that's nice to access immediately. And that's the backbone for getting as much information as we can over the network. Thanks for watching.